I'm Bryan Kolb from the University of Lethbridge, which is in southern Alberta. If you've ever heard of Calgary, it's not far south of Calgary. And my job is to moderate this session and the next session, even though Marla tried to boot me off moderating this section just a minute ago and was going to have Russ do it. And you didn't know that, did you? Neither did I. Okay, which machine is the slides, Marla? Is it this one? Okay, whoops. The topic of our session is how do social signals and stress change the brain? And the answer to this, the simple answer, and you can leave, and we won't have to listen to Michael tell us. You're late. They influence brain circuitry and the capacity for further change. And so basically what I'm going to suggest to you is that one of the things that these factors do is alter the way in which the brain responds to subsequent experience. That is, alter what I'm going to call brain or neuroplasticity. How do we measure this? And this, I'm just giving you an overview here. There are various ways of measuring it. The most difficult way of measuring this you've just heard about in 3 of the previous talks, and that is behavior. There's no question behavior is the hardest thing to measure, and as we go down the list, things get a little bit easier to measure and a little easier to quantify. We can do it with neurophysiology. We can do it with neuronal morphology, and I'll say a little about that. We can do it with epigenetics, and you've heard something about that. And finally, we can use other molecular measures, and you'll hear about that from others. So, just as an example, if you were going to try and make life stressful for a pregnant mother, what might you do? And the idea is that you could use 2 different if you're a rat, you could do it in people too. You can use 2 different kinds of stressors. One kind is physical stress. The other kind is psychological stress, and the effects are surprisingly different in many ways. One is that the amount of stress measured by cortisol levels or corticosterone levels is different. If you look at physical stress, you can actually constrain animals, put them in tubes, or put them in cold water for a few minutes and make them swim around in this cold tank of water. So if you had a pregnant rat, you could put her in, let's say, in the 2nd week, which would be equivalent to beginning of the 2nd trimester or so, or late in the 1st trimester in humans, and stress her for varying periods of time, daily usually. The other way to do it is to use what I'm going to call psychological stress, and that is to simply take a rat and put them on a little platform in the middle of a room, and there's nothing else there except the experimenter sitting in a chair watching. And the rat is very stressed by this because when's the cat coming, when's the eagle coming, and so they don't like sitting there. So 15 minutes on that platform, the cortisol levels go through the roof. So the effects are going to vary with how long they're on this platform and the severity. But the key thing here is, what does it do? So if we look at moderate stress, one thing you get is a Mac PC discussion here over. You get smaller brains in the offspring. So we're now looking in the offspring when they're adults. So your mom is stressed for 1 week. You're in utero, you have a week to recover in utero still, then we look in your brain when you're an adult. And we see small brain, we see larger adrenal glands, we see decreased numbers of synapses in the orbital frontal and medial frontal cortex. One of the things I was struck by this morning was Clyde talking about prefrontal cortex. I bet 5 years ago he didn't know where it was. So this is an amazing progression. My hat's off. In the rat, there are 2 basic regions of prefrontal cortex. One up here, as there is in us, and one behind the eye. So this would be, I'm going to call medial. The other one is orbital. They have different functions. Don't worry about those functions right now. We see abnormal social play, and I'll come back to that in a second. So the play behavior has rules, and they don't follow the rules if they're prenatally stressed. And we have changes in cognitive and motor behavior. If we look at mild stress, we again see smaller brains. We now see, however, a different pattern of synaptic change. Instead of decreased synapse numbers in those 2 prefrontal regions, we see an increase in the medial frontal region. This is not what you see in adults either. And you see a decrease in the orbital frontal region. We again get abnormal social play, but the abnormalities are different. And we see increased anxiety. Now, if we look at gene expression, and what we did here was partly from Michael Meany, and that was he drones on and on about hippocampus, but some of us are frontal lobe chauvinists, and I was convinced that the changes in gene expression in hippocampus and frontal lobe might not be the same, and they're not the same, as you can see. This is the number of genes that are whose expression has changed. So again, you're an adult and you had this experience in utero. You can see on the left, in each case, are the males, on the right are the females, and at the top are changes in hippocampus, and the bottom are frontal cortex. The take-home message is a lot of genes change. There are different genes changing in different places in the brain, and it's sexually dimorphic. Males and females show different changes, and the frontal cortex and hippocampus shows different changes. So if when you look at, say, changes in methylation in blood as a surrogate, it may not be a surrogate for different regions of the brain. In fact, they're quite different. And we have methylation measures as well, and they're different. So what? Well, what this means is that if the structure of the hippocampus and the prefrontal cortex are changing, then the circuits are changing, then the functions are going to change. And the way, and going back to my original point, the way the brain's going to respond to experience later in life is now going to change. We're not going to respond in the same way. Well, what about social experiences? Because this session includes both stress and social experiences. I'm going to give you 3 examples of social experiences. The first one I think is kind of cool. We discovered it entirely by accident, but we'll pretend we planned it because that's better. So what we did was we had 2 pregnant females living together. We had many pairs of 2 pregnant females living together. But in one condition, one female was taken away for the psychological stress every day. So she was taken away for 15 minutes, placed on this platform, and brought home. When she was brought home, what happened was that she started singing a distress call, and she would sing that distress call for about 3 hours. Her cage mate, who was not directly stressed, would sing back a happy song for the same 3 hours. So it's almost like, I'm being really anthropomorphic, I'm out, I'm getting stressed, I come home, life is shit. And your mate says, no, everything's good, all cool, you're okay. And so you've got this dynamic going on. The scary thing is the whole colony can hear that, and we hadn't really thought about that very much. Anyway, so that's the what I'm going to call bystander experience. Now, what happens when you do that? Well, it turns out that you change the circuitry in the entire brain. Now, we're looking again in adults. So the bystander animals have an increase in spine density. It means they have more connections. That isn't necessarily a good thing. It means the circuits are changed, but they're changed everywhere. They're changed in hippocampus, they're changed in frontal cortex, they're changed in visual cortex, and so on, just from this experience for a week prenatally. If you look at gene methylation changes and gene expression changes, you see a thing that looks very much like the previous Venn diagram that you saw. It's sexually dimorphic. Males and females change differently, and we see it's different in hippocampus than it is in frontal cortex. What's interesting here is that almost all these genes are shut off, which is different than in the stress where there's an equal number roughly of genes being turned on and turned off. Here they're being turned off. I'm not sure what that means, but it clearly has implications for the function of the system that's been changed. This is looking at maternal separation. This is work done by others. And in these dagus, which are great, these dagus have an advantage in that they have biparental care. So both the male and the female look after the infants. And so you can simply look at changes in the presence or absence of the dad. So we just take away the dad, and we'll now have an aunt help or no help. And it turns out that what you get here, if the dad is gone, it doesn't matter if there's an aunt there. Not the kind of aunt that Joel was talking about, but an AU aunt, right? And you can see in both, in adulthood as well as at weaning, you can see that there's a decrease in spine density, therefore a change in the neural circuits in the orbital frontal cortex. These authors didn't look in the medial frontal cortex. My prediction would be it changes too, although who knows what the change might be. If you look at maternal separation, so what we're going to do now is we're going to, after birth, take the mom away for an hour or 2 hours or 3 hours, and what I'm showing you is just 1 hour a day for 10 days postnatally. And what we saw is smaller brains again. We saw a decrease in the number of synapses in orbital frontal cortex and an increase in medial frontal cortex, which was the same thing we saw with mild psychological stress. We see changes in play behavior again, and we see changes in anxiety. So it's the same as the mild prenatal stress. We also see changes in the response to psychoactive drugs. The animals respond in a different way. There's a more extreme response to psychomotor stimulants in these animals as adults than would be the case in animals who are not stressed or not separated. Play behavior is wonderful. All mammals engage in play behavior. And one of the neat things about it is it has rules, and the rules are species specific. So if you're a rat and you're playing, you're like, it's the same kind of game as a kitten plays. So I'm a rat, and I want to play, and I'm the guy on top here. What I'm going to try and do is nuzzle the back of the neck of the other guy. So there I am. Oh, here I come. And the other guy's going to say, don't think so. And so what we get is this pushing and pushing, and we get this sort of popcorn behavior where they're rolling and jumping and zooming around just like kittens do. Kittens do exactly the same thing. Sergio Pallas is one of my colleagues, and he's arguably the world's expert on play. He did his master's on kittens, and he's studied 57 species of primates now, and he's looked at an enormous number of animals. Kittens and rats do the same thing. Okay. What can we do with play? We can manipulate play. What we're going to do is we're going to allow animals to have a lot of play or not very much play. Now, I know you can see through this. What I did, obviously, was blow up the little ones and make them big ones. So what we can do is take a rat that's weaned and have it live with an adult or 3 adults or 1 sibling or 3 siblings. Adult and infant rats don't play with one another. So you get lots of social interaction, but it's not play. So the question is, what happens? And the answer to this, when you look, we manipulate this during the juvenile period. We then look in adulthood to see what's happened to the organization of the brain, and it turns out that the prefrontal cortex is totally reorganized by this play behavior, that is, the absence of play behavior. And the curious thing is that we see a reduction, a simplification, if you like, in the number of synapses in the medial frontal cortex related to the amount of play, but the orbital frontal cortex is responding to the amount of social interaction. It doesn't matter whether you're playing, it's how many conspecifics live with you. Now, this is pretty interesting because it suggests that what we'll see is a change, for example, in drug response in adults, because the prefrontal cortex is the most sensitive region of the cortex to psychoactive drugs, and we do. And it turns out that the amount of play behavior that one's allowed to engage in changes cognitive behavior, changes motor behavior, and it changes response to drugs. And so our belief here is that what's happening is play behavior, the role or the importance of play behavior is to make the brain plastic. If you don't get to play, the brain becomes less flexible in adulthood. So it's a kind of phrase we used to call play problem solving, and I think in many ways that's exactly what it is. We're solving problems with play. Okay, so I've given you an overview. We're going to talk about social systems. We're going to talk about stress. We have 3 speakers. Well, the conclusion is that. We have 3 speakers. Russ Fennell, who's a professor of biology at Stanford, will begin, and he's going to talk about this wonderful system in fish.